Alright, so we are live. And hope everybody's doing well. Any other questions? So I mentioned this in Open Lab yesterday, but since that was optional, not everybody was there. So Wednesday when we were playing with synchronization, I mentioned that you can synchronize methods as well as blocks of code, and there's a keyword synchronized you can put in the description of a method. And when we tried to do that on Wednesday, when I tried to do that on Wednesday, it didn't work. And the problem was I was trying to synchronize a method inside the mythread class, which means that MT1 and MT2 were running their own basically versions of that method, and the synchronization wasn't working the way it was supposed to. So what I did was I changed that to have the threads use a method in the parent object, right? So parent.increment tally. And so now both threads, even though they're separate executions, are using the same method. And that method called increment tally has a synchronized keyword. And if you do that, then you get this nice synchronization of the threads. So when you run this, you get final tally of 20,000, which is what you would expect. Whereas if you take out this synchronized keyword, then you get that unexpected behavior where the two threads are executing the increment instruction at the same time and conflicting with one another. So that synchronized is a useful keyword for a method if you really want to synchronize an entire method. But again, I'll remind you, if you don't need to synchronize a whole block of code, don't. Synchronize as small a block as possible because you're trying to have your threads execute simultaneously, and synchronizing really deliberately short circuits that and says, okay, even though we've got multiple threads, only one of them can run this at a time. So do that just where you have to avoid some of the things we're going to talk about today. Could you go over why we have to flush print writers again? Sure. And this is a general concept, which is when we do system out print line, or in C when we say print F, or any kind of sort of high level output operation, usually intended for human consumption. So you can say print, and this is also if you're going through a print writer. Here's your output device. And when you print, it doesn't go directly to the output device. It goes into a buffer. And the output of that buffer feeds your input device. So you print hello, and HELLO goes into this pipeline, but it doesn't go to your output device yet. And then you say cool, and cool goes into there. It's not actually backwards, I'm just drawing it. So the stuff that you print through a print writer or through system out print line or printf in C kind of goes into a holding area in memory, and it stacks all this stuff up. The reason being that to actually send these characters to a display or a file or something like that, fairly expensive operation. You got to talk to hardware, you got to synchronize things like that. So generally when you write, it gets buffered up in memory. And this buffer will get pushed out to the actual output device in certain cases. For example, typically, if you output a new line that says, go ahead and take everything that's buffered up, send that out. If you do a close, in some situations, that will also force your buffer to be written out. With print writers, it doesn't, but with doing fprintfs to a file in C, that will do it. The other thing is you can do flush, or in C it's fflush for chapter 3 manual functions, and those say force the buffer out. So yeah, it's all about the buffer. This happens all over the place in computers, right? It's an issue when we're printing things from our programs. It's also an issue when you open a file and you make some changes. Let's say you're in VI and then you say :WQ. Well, that writes the contents of the file you just edited, presumably to the disk, but in practice probably not. It probably goes into a holding area, a chunk of memory somewhere, and has not been written to the disk yet. And if your machine suddenly crashed right that instant, your changes might not be on the disk, because there's a buffer between the file operations we do and the actual physical hardware. And so in Unix, you can do the sync command, which says take all of those buffers and write those out. And when you shut down a Unix system, it always does a sync to force those buffers out. And it's the same story as updating something on a flash drive and then pulling the drive out without doing an eject. The eject oftentimes will do something like a sync to actually say, okay, all those things that you thought you wrote to the flash drive, go ahead and actually write those, and then you can pull it out. Good stuff. All right, other questions? You want to do timing diagrams for 2-bit adders? Sure, yeah, I like timing diagrams. When you start writing timing diagrams for C or Java code, you're having a good day. Well, let's keep talking about thread safety and about issues we can get into. So we know one issue is resource contention. If we have a read modify write happening between two threads, and let's say they both read at the same time, and then they both modify, and then they write. This write will replace that write. And this write is based on the read before this write happened, and so in effect, this read modify write gets undone. And so this is why when we increment our tally 20,000 times, the final tally is smaller than 20,000. So that's one possible problem, and we can get around this by using some kind of synchronization. And there's lots of things we can say about this, but there's concepts of mutexes and semaphores. And after a few decades of doing this stuff, I'm still not sure I could tell you decisively what the difference is between a mutex and a semaphore. I mean, I can read you definitions, but these are things that are basically different approaches to doing something like saying, hey, I'm going to access this object. Is anybody accessing it right now? And if so, I'm going to wait. If nobody is accessing it right now, I'm going to make exclusive access mine. And I'm going to do something so that I can start using this shared resource, and anybody else who wants to use it is going to have to wait. And so all of these things that you'll get into later with p threads and mutexes and locks and so on are all different versions of that. So that's one issue we need to deal with, which is just making sure we don't step on each other when we're trying to share memory. But there's this whole separate set of um, of issues, which is the possibility of needing to share resources and getting in each other's way. So we started to talk about dining philosophers. And so 5 philosophers, 5 chopsticks, 1 infinite bowl of noodles. And we were asking what algorithm could we describe so that, philosophers can eat and talk and nobody starves. And the main rule was to eat, you need to have a pair of chopsticks. So if this philosopher is going to eat, they need to acquire the chopsticks on either side of them. And then they can eat for a while and then put the chopsticks down. So we looked at one initial algorithm, which was, kind of a first naive approach, which is, see if there's a stick on the left. If there is, pick it up. See if there's a stick on the right. If there is, pick it up. Eat, put your sticks down, talk, go back to the top. And, the immediate problem there is that if all 5 philosophers begin that algorithm at the same time, each will pick up the stick on their left, and then nobody will be able to pick up the stick on their right. And there was nothing in that algorithm which said, to do anything other than just keep waiting for the stick on the right. And so that's an example of what's called deadlock. You have, say, 2 threads, and each is waiting for something that the other thread has, and neither will release their resource until they get the resource that the other one has. And that's a really typical problem with multi-threaded applications. So what other approaches could we use for this? Anybody come up with any ideas? You could have a timer. So what could we do with a timer? So you could make a schedule, right? We could say, okay, you get to eat, at 1 minute past, 2 minutes, 3 minutes, 4 minutes, 5 minutes past, and we could just take the time modulo 5, and each one gets a slot. So we could have a schedule, and that's one way to deal with this. So yeah, TDM, time division multiplexing. So that's one way out of some of these issues. And if we gave each one a separate time slot, we're guaranteed that everyone's going to eat and everyone's going to talk, but we've lost our parallelism. But we could expand that idea. For example, we could say, at time 0, these 2 philosophers will eat. And then at time 1, these 2 could eat. And then at time 2, these 2 could eat, and so on. So we could have some parallelism, right? Because, philosophers that aren't next to each other don't share a chopstick. So you could, just sort of go around in a schedule like that and have them eating in parallel. I've decided I'm not buying organic bananas anymore because they come with fruit flies. But my bananas are long gone. The fruit flies are still here. So that's what you see floating around sometimes. All right, so well, that's kind of what time division multiplexing is, in some sense. You could split the chopsticks in half, or you could, yeah, but we're not allowed to break the chopsticks. You're not allowed to bring in your own chopsticks. So yeah, if some philosophers are not hungry, then the time slots get wasted. So someone pointed that out, and that's actually a really good point. That in this example, we're assuming philosophers want to eat and talk continuously. But if you think of these as, jobs trying to use, say, a shared network resource or a printer or a slot of memory or something, right? If we allocate time slots to these, what happens if, it's this philosopher's turn and they don't want to eat? And what if, there's some moment when three philosophers really, really, really want to eat, and even though it's not this one's turn, right? We'd like them to have a shot at executing, or maybe this one always does something that this one depends on, but with this schedule, once this philosopher eats, this philosopher doesn't get a shot for another 2 or 3 time slots. So scheduling is a nice way to get out of the quandaries of sort of asynchronous, semi-random execution, but sometimes it's that asynchronous, semi-random execution that we're after, right? We want our jobs to run as quickly as possible, and we can't predict ahead of time when these jobs are going to be ready to execute. So typical example is, our Linux server. You have 10 people logged in, or an assignment's due, so we have 20 people logged in, and they each want to access the hard drive to, compile their program. And whoever comes first should definitely get first shot at it, but what about the people who come in and try to use the hard drive while somebody's already using it? And fundamentally, your hard drive may be a single resource that can only be accessed by one process at a time. Now that process is the operating system, and it's taking in multiple requests and using its access to the hard drive to, share these requests among multiple users. Yeah, it seems to keep coming back to deathmatch. So another way around this is to have, a wait person, have somebody who comes in and basically says, okay, you and you can eat for a minute, right? And have an arbitrator there. So that's a centralized control. And that's another approach which might work well for people dining, but might not work for, a system running 100 processes where we don't know how to, from some central location, decide which process should execute next. Yeah, fruit fly action. 2 go in, 1 come out. There you go. Yeah, maybe. Nice, we got poetry going too. That 10 times fast. Whoa. All right, what else can we do? Uh-oh. Priority queue. So if we can prioritize these jobs, then that might relieve some of this contention. If we prioritize them absolutely, if each one had a different priority, then we could simply say, the hungry philosopher with the highest priority gets to eat. And you could check to see, if the second highest priority philosopher has chopsticks, and if they do, they get to eat also. But by using those priorities to order the operation of picking up chopsticks, right, we could probably avoid some of this deadlock situation. So for example, let's say that this is the highest priority, right? At the beginning of execution, the beginning of the meal, this philosopher could try to pick up both chopsticks. And assuming they succeed, they begin to eat. And now, after they've already taken their resources, the second highest priority attempts to eat. And maybe that's this philosopher here. They can try to get the stick on the left. They fail, so they pass. And now this philosopher tries to eat, and they can get the left and the right, and so they succeed. and this one will fail, and this one will pick up the stick on the left but can't find the stick on the right. So they put down both sticks and they wait for some period of time. And if they all have the same priority and go in the same queue, it's essentially round robin. So this is getting into operating system notions, right? So if you take an OS course at a university, you'll study different scheduling algorithms and different ways of sharing, say, a CPU among multiple jobs. And one approach is round robin. You just order your jobs based on maybe the order they came in, and just give each one a slice of time, and just keep going. Another approach would be to use priorities. Another approach would be to use some kind of estimate of which process needs the least amount of time. And if you have some way of knowing this job's only going to need, this much time, and this one needs a lot, you give that short job a first shot at the CPU. All right, so so those are all good, but they sort of require external control and some kind of differentiation among the jobs that has to be done somewhere up front. If we have identical philosophers and we have no central control and so on, you can try other algorithms. For example, you could pick up your left stick if it's available, and then pick up your right stick if it's available. And if the right stick is not available, put down the left stick and wait. Wait, some amount of time, and then go back to the top. And try to pick up the left. If you can, try to pick up the right. If you can, eat. If not, put both sticks down. Yeah, that's my banana fruit fly. Someone said it's looking for noodles, so it could be. Journey of 1,000 miles, right? So I just got to start evicting my fruit flies one by one. I hope I can keep ahead of their reproduction rate. All right, so that one's outside, checking out Harry's locksmith. Yeah, I don't want to kill him though. But I've heard that approach works. All right. So check for a left stick. If you find it, pick it up. Check for a right stick. If you find it, pick it up and eat. If not, put both sticks down. And now we can avoid this deadlock. Because if they all pick up their left sticks at the same time, each is going to look for a stick on the right, not find it, and they're going to put down the left stick that they picked up. And now potentially, somebody else who needs that stick may be able to pick it up. But this can still lead to an effective deadlock where if they each try to pick up the stick on the left at the same moment, and then they each check for a stick on the right at the same moment, they're going to continually find, I don't have access to the stick on the right. They're going to put down the left stick. They're all going to wait for 17.2 seconds, and then they're going to do this again. And so this is live lock. Deadlock, you can kind of think of processes moving from step to step to step, and they get stuck at some step, and they can't move beyond that. Live lock, you have a process that's moving through some steps, and sometimes it goes back and it does some other steps again, and so on. But there's some point beyond which it never passes. And one place we encounter this, I let them live rent free, and I give them bananas apparently. If say you're walking down the sidewalk and somebody is walking towards you, and you meet, and your algorithm is wait until the person moves aside and then go forward. Okay, so my algorithm says wait till this person moves and then I'm going to go forward. And this person's using the exact same algorithm. Wait until the person moves and then go forward. Right? We're deadlocked. We're each waiting for the other to do something, and the other is not going to move until we do something, and no progress gets made. You just stand there and stare at each other. All right? A different algorithm is if you're walking down the sidewalk and you encounter someone directly in front of you, move to the other side. Well, if you both have that exact same algorithm, what happens is you both move over here, and you can't move forward. And so you apply your algorithm again, and you both move over here, and you can't move forward. And it's a different situation, but the same effect. That's more like a live lock situation, where you're changing state, but you're not advancing in your algorithm. Right? So yeah, that's where you're doing that dance. Nice. But what if your friends don't dance? So this was a thought exercise from Dijkstra, right? And it looks at things like deadlock and live lock and starvation. So starvation is a situation where you might have, 3 processes or 5 processes executing, and some of these processes are making progress, but some of them never manage to make progress. Excellent. So that's apropos to dining philosophers, right? You might have an algorithm where it ends up that these 4 philosophers can eat and talk and so on and so forth, but for whatever reason, based on your algorithm, this one never gets a chance to eat, right? So maybe you're just swapping between these 2 and these 2, and so you have a starvation situation. And in operating systems, starvation would be where you had one process that wasn't getting any or getting enough CPU time compared to the others. So these are all situations that can happen. Now, if you identify your philosophers, if you give them each an ID, you can come up with algorithms that will get you out of this. There's a solution to this that I read once that involved having clean and dirty chopsticks, where you could use the process of cleaning a chopstick after you finished eating it to help resolve the deadlock that you might get, and so on. So you can read details of this, and there's lots of discussion about it, but it's a thought exercise, and it informs some of what we do today with operating systems and process control. All right, so questions about that? Awesome. So just kind of for comparison, let's look at some of this in C. And we talked a little bit about processes in C back in 224 when we looked at fork and execl, and we were looking at popen and system and things like that. Let's brush off a little bit of that and just see what this looks like. So here's a really simple attempt at yeah, cobwebs for sure. Here's a first attempt at making a pair of processes. So remember the call to fork. When you call fork, it creates a clone of the current process, and the clone is an exact copy of the current process except for the return value from fork. So if fork returns a 0, it means you are the child process, you're the clone. If it returns something non-zero, you're the parent, and what was returned was the process ID of the child. So typically after we call fork, we can check the return value, and if it's 0, we know we're the newly created child process. If it's non-zero, we know that we're the original. So I have my integer tally, and I'm going to call fork, and if fork returns a 0, I'm going to identify as the child, and I'm going to loop some number of times and increment tally. And then I'm going to say, I'm exiting. Let me go ahead and say child process exiting. And I'll tell you what the tally is, and I'll return. Otherwise, I was the parent, so I'll go ahead and do the same thing. And I'll say parent process exiting. So if I do that, I exit and the tally is 10 in both cases. And if I make that number of iterations 100,000, I exit and both reported a tally of 100,000. And this is not a problem. When you execute a call to fork and you create a clone, you get an entire separate copy of the whole essence of the parent process, including your own memory space. So the child process actually has its own copy of this tally method. So we have two threads, but they're not sharing memory. And in Java, when we create a thread and we start it, it is in the same memory space as everything else. So our stuff is kind of by default shared in Java, but in C that doesn't happen. Now we can make that happen, but by default, when you clone a process with fork, you've got your own memory space, and I could do anything I wanted to my variables in this child process, and they're going to have no impact on what happens in the parent process. So child parent. All right, so I don't want to get too gory here, and this is stuff you'll do in like system programming courses elsewhere. But let's look a little bit at shared memory here. So SHM get. Yeah, no, code is good. SHM get, so System 5 shared memory segment. So we can basically ask the system when we run a C program to create access to a chunk of memory that's accessible from multiple processes. And so SHM get will do that. So I'll ask for a private chunk of memory. I'm going to ask for 32 bytes, and I'm going to say, allocate that memory, and this is our permission 666, which makes it readable, writable to everybody. And then yeah, I know, but it's octal, so it's okay. And then so I'm setting up tally as a pointer to an integer, and I'm going to set it equal to this SHMAT, which is allocating or attaching to that shared memory. So we're not going to worry about the meaning of this mechanics, right? But basically, this creates a shared memory space. This attaches my pointer tally to that shared memory. So when I do this, right, tally is going to be a pointer to an integer. When I do that attached down here in the parent process, tally is also going to be attached to that same shared memory, right? So this is creating a chunk of memory that will persist across the fork, and then in each process, child and parent, I use that shared memory for my tally. So let's go ahead and run this. Right, and so one of them, so I'm just printing out the value of that tally object, and you can see it's the same memory address. And the first processed exited and tally was 10, and the second exited and tally was 20. So this is what we were seeing when we had two threads in Java and we were incrementing from both of them. So these processes run independently of each other, but they each increment the same location in memory, which is an integer, and since they each run 10 times in this case, when they finish, we should have a final tally of 20. And if we try to increment 1,000 times in each process, right, we get 1,000 and we get 2,000. So that looks like it's working really well. Well, it's working really well because C is fast, right? Yeah, they're not synchronized. We're just kind of lucking out here. And if I bump this up to 10,000, right, we're still lucking out. But if I make this too big, like 100,000, right, then we start to see some problems. And so the same thing is happening that happened with our threads in Java. If I ask this loop to run 100,000 times, that's long enough that each thread is going to get interrupted, or is going to be, executing that increment at the same time that the other process is executing that increment, and they can conflict with one another. And if I make this even bigger, right, then we're just getting, lots of conflicts, because this should be 2 million, and it's barely breaking 1 million in some cases. Hashtag clobbered. All right, so what do we do about this? So we introduce a mutex, and a mutex, like I said, is like a flag that basically lets us say, I would like exclusive access. Let me know when I can have that, and then as soon as you get exclusive access, nobody else gets that access. So definitely not going to get bogged down on mechanics, but we include a few more things, and we create this structure, and I bundled this up into a couple of functions. So this is the same shared memory code that we had before, but I'm going to do two other things in here. First of all, I'm going to do some initialization to create a mutex which will be shared, a flag which will be shared by these two objects. And then before I do my increment, I'm going to say, let's get an exclusive lock, and then let's release that lock when we're done. And then this is just, horrifying C code, the way system level stuff always looks when you write it in C. But this is the initialization, right? So you set up a memory map, and you assert your object and, stuff. Don't worry about that, right? And then the locking and unlocking we just call functions that are part of pthreads, and so pthread mutex lock and unlock, and this is a shared object basically. And so the effect will be, once we initialize this, that if I call lock from this process, and at the same time this process tries to call lock, this is going to block. It's going to have to hang out and wait. They get called after the return. I'm not sure which return. Oh yeah, so I was short circuiting. Good, thank you. So yeah, we'll do these locks and then return, but then I'll put those back in the beginning to see what happens if we don't do that. So let's go ahead and run this the way. And we have to link in the pthread library, right? So if we run this, it ends up being rock solid, right? So the final tally will be 2 million every time. But, you know, if we don't do this locking, so if we just turn this into, you know, a no-op, right, we get this contentious result. And so you can play with this, right? I mean, we can do this as kind of an all or nothing and see, you know, bad things are happening or good things are happening. But you could do things like, instead of just incrementing a shared object, right? We could throw a sleep statement in here, and you could see, you know, one process waiting for the other one to unlock, and so on and so forth. Um, and so, you know, some other classes you might code up the dining philosopher problem and or make a process scheduler and see how different algorithms work and so on. So I'm not going to dig any deeper into, you know, these details. But, you know, if you're interested, um, take a look at you know, do a man-keyword pthread, and there's all of this stuff in here related to pthreads. And this is one way to manage multiple processes that lets you, you know, synchronize operations among them and so on and so forth. Yeah, it's a big I was gonna say wormhole. I don't think that's really a thing. Maybe it is. And there's different approaches to this, but as we mentioned the other day, you almost always need some kind of low level support to do this locking and synchronization. It's really hard to do it yourself. If you try to use a software flag, then you have to make that process of checking and updating the flag atomic. Um, yeah, that's true. All right. So questions about any of that? Yeah, it's a lot to absorb. But you know, this is a pretty high level pass over something that, you know, could be an entire course at a graduate level, right? So there's a lot going on, but just kind of first pass over it, and, you know, I'm definitely not going to ask you about the C stuff on an exam or something, but high level concepts of synchronization and you know, managing threads in Java. That's the main thing I want you to get out of this. All right, so let's take a few minutes and try to log into Canvas. So let's touch base on SLP and quizzes. So don't forget to do your quizzes. There's like 3 quizzes out there that you should be able to do. But make sure you've done those. Let's talk about the service learning project. So your final upload is due on June 7th. Okay, so it's about a week to get that done, and that's also the day of your presentation. So we'll talk more about the presentation next week. But let's just talk about the final upload. So your final upload is a formal report. Okay, it's not a one-page list of questions with a sentence written next to each one. It's a report. Okay, this is something where, imagine that you went to an investor and they gave you $1 million to work on your SLP. This is what you give them in exchange for that $1 million. Here's the report on what I did over the past 2 quarters on this project. So a few technical details. I want a report from each person, but if you're working in a group, you can turn in a single report that's identical for each group member. But each group member has to upload the report. If you don't have your PDF in Canvas, right, it's a 0. So even if you're doing the same report, make sure each person uploads it. And then details on report requirements. All right, this is a template. This is the stuff that you need to have in there, but again, it's not just, 1 dot, 2 dot, 3 dot, right? Make a report like a lab report, okay? Title page, abstract, table of contents, introduction, objectives, things like that. A full-blown thing that stands on its own and should cover at least the following, right? Detailed description of the problem you're trying to solve, the scope of your project, right? You're trying to make a game. What does that mean? Were you making the game engine? Did you make the physics engine? Did you use Unity? That kind of stuff. And then the parts and pieces that we've done before, for the posters and stuff. So objectives, alternate solutions. This is your research into, other things that address the similar problem space. What are you doing that's different? What are you doing that's similar? And so on and so forth. Solution specification. This is going to be many, many pages. This is your circuit diagrams, your schematics, your system diagrams, your code, your pseudocode, your flowcharts, your outlines, your user manual, right? All of that stuff. Basically everything that completely describes what you did in enough detail that somebody else could reproduce your solution. Verification, test plans, experiments to test the system you came up with, the results of testing it. Did it work? Did it work partially, completely, and so on. Future plans. If you were to keep working on this, what would come next? What would you change? What would you embellish, and so on and so forth. Lessons learned. Right, so this is sort of the takeaway from having worked on this throughout 2 quarters at Clark. What did you learn from this? Including, I learned how to use, the Unreal Engine, and I learned some C++, and I learned about using blueprints and so on and so forth. But also, I learned that time management is really tricky. And I learned that, I don't have as much time as I thought. And I learned that if I don't set hard deadlines, I tend to not do things until the last minute, so all of that stuff. And then very, very important licensing terms. So here you get to decide, do you want, so you're going to turn this report in to me, you're going to turn it in through Canvas. Do you want me to keep that as privileged, protected information, or are we allowed to share that with the world? Okay, so if you want to do this as an open access project, you can use something like this, right? Permission is hereby granted free of charge, etc., etc. If this is something you consider proprietary, if this is something you might want to commercialize, if this is something you just don't want to share with anybody else, just tell us that right here. Okay, say, this is my private property, and you can use this report for grading, but for no other purposes, and you can't show it to anybody, etc., and we'll treat it accordingly. Okay. Otherwise, if you give us permission to make this freely available, some selection of these reports may get posted to the website by Izad and myself, and may get shared with other people. The foundation is using some people's projects from a few years ago as part of their marketing materials now. Projects that were said you can use this for anything you want, and so on and so forth. So make sure you include license terms for me as I read your report. All right. So think about that. If you have any questions, let's talk about it on Tuesday. Monday is a holiday. There's no classes at Clark, so we won't meet Monday. I don't have office hours Monday, but Tuesday will be business as usual. So have a great weekend. Good luck with your stuff. Do something fun, and I will see you on Tuesday.